Welcome to another notes. Last time we talked about mineral identification part 1. Those 4 properties we talked about last time were color, luster, streak, and hardness. Just a little recap on each of those, 10 seconds each. Remember, color is the actual physical appearance. Is it green? Is it blue? Don't be deceived though, there are a lot of minerals with the same color. Remember, I gave you those 2 green ones that were the same. Luster is how shiny or dull something is. So diamond, quartz have a high luster, whereas that hematite, which was kind of earthy and dull, really not very pretty. Hardness is exactly like it sounds. Can I scratch it with my fingernail, or do I need something harder like a nail to kind of break it apart? And then streak is going to be what color does it leave behind, what color residue. And then I gave you the example with the steak. Your steak might be brown on the inside, but it's pink on, or outside, excuse me. But it is pink on the inside. So you just have to be careful with streak, and that's going to be one of your key characteristics when identifying minerals. So today we're on part 2. You're going to be talking about cleavage and fracture, density, and special properties. So we're going to start with cleavage and fracture. So sometimes the way a mineral breaks provides clues into a mineral's identity. Just like when you break a bone, let's say you're in a fight or you're in a car crash, a doctor can look at your bones and he or she can kind of determine, well, was the collision from the side? Was it head on? Did it happen from a blunt force trauma, like someone punching you in the face? We can look at broken bones and we can kind of determine and figure out exactly what happened, whether your story is truthful or not. It's the same thing here with minerals. So what's going to determine how it breaks, though, is the arrangement of atoms or ions. Remember, ions are charged atoms. And the strength of their chemical bonds. So you have 206 bones in your body. Arm bones are pretty skinny. They're kind of easy to break. That's why a lot of little kids fall out of trees and they break their arms. But you very rarely see anyone break their femur. Okay, that's your thigh. That bone's huge. It takes like 2,000 pounds of force to try and break it. Just because of the actual thickness of the bone itself. So the same thing here. The atoms are going to be stronger with certain minerals and then weaker with other ones. So minerals will break in between atoms. Think about when you're ripping something. If you fold a piece of paper in half and then you go and try and rip it, it's going to be a lot easier to fold or rip, where you folded it. It's the same thing here. You can see in this mineral, I believe it's calcite, you can actually see some like segments already. So right here we have it already kind of breaking apart. Going this direction, we already have it breaking apart, and going this direction, up and down here, we have all sorts of slits that are already kind of there, showing, hey, this is where it's weak. This is where the atoms or ions are not super strong anymore. So if a mineral breaks smoothly with a flat surface, it's said to have cleavage. Calcite has cleavage because it breaks along 3 directions of it, actually. Here's another picture of calcite. This one's a little tougher to see the cleavage, but you can see here's a nice straight line. So right there is where it's going to break really easily. Same thing here. This is pretty much a pretty hard line. There is a site of cleavage. Same thing here. This line is a site of cleavage. You're going to be able to smash this thing with a hammer and get pretty nice even cubes, which is another word for cleavage. Okay, same thing here. You're going to get those nice clean cuts. Here are some examples of cleavage. Okay, so you have cleavage in one direction where it's just a bunch of plates stacked on top of each other, basically, like this guy here, muscovite. Cleavage in 2 directions is a little more like puzzly looking, but it can break this way or this way. Like feldspar, that's a lot of earth around you. Halite is salt. Halite has 3 cleavage directions, all sorts of funny things. And then calcite actually just gets kind of curvy. It looks like you wrote it in italics. Okay, calcite can actually break in 2 directions, but it's like a slanty 2 directions. So kind of fancy. You won't necessarily need to be able to tell me how many directions it has. However, I know this one is super easy to tell because it kind of pulls apart like layers of cake. Okay, or like 3 pancakes stacked on top of each other. It's super easy to just pull one pancake off the top. The rest of these would require a kind of hammer and a smashing action to get this shape. But the pancake one I know is super easy to see. It's cleavage and fracture. So cleavage is when it's nice and smooth and even. Fracture is just like a bone. If you shatter or fracture your leg due to a car crash, it's all over the place. You don't have a nice clean break. You don't have a nice even split. It's kind of just willy-nilly in your leg. So quartz is that. Quartz breaks unevenly because the bonds are equally strong in every direction. So you're going to take a hammer, smash down on that quartz. You're going to get some big chunks, some round chunks, some long chunks, some short chunks. They're not really going to be nice and even. So when fracture happens is when a mineral breaks and forms uneven surfaces. Think of fracturing a bone, fracturing a relationship, you and your best friend. It might have some jaggy edges. Someone might be a little extra hurt and someone might not be quite as hurt. So fracture is when things are uneven. Fracture patterns are unpredictable. If I had 10 samples of quartz and I smashed them all with the exact same hammer, I'm not going to get the same 2 pieces every time. It might be big and small, 2 mediums. It's very unpredictable. There's no easy way to say, hey, I guarantee this is going to rip off like a stack of pancakes. Okay. Some break into splinters or fibers. Okay, you can kind of picture what both of those would look like. Fibers are just going to be long, stringy things, and then splinters are just going to be tiny little parts. Others break like thick glass with smooth, curved surfaces. So I know you see that word smooth and it's maybe throwing you off a little bit, but it's curved. Cleavage is straight. Okay, so fracture is when it's curvy. So if you took this guy here, I forget exactly what mineral this one is, and that's my apologies. If we took this and it's just showing you fracture, but I still don't know what mineral it is. You can see it's jaggy. It's not very nice. It's not very even. There's no side that's smooth or nice and just flat. So that was smashed by a hammer or something, and it was fractured like a bone. Density, I know we have practiced this through and through. We've done 2 labs. You took a bunch of quizzes on it. We should understand density by now, but just in case. So think about picking up a bowling ball in your right hand and a volleyball in your left hand. So go ahead, picture it. Feel the weight. What did you expect to be heavier? I assume you're going to say the bowling ball. Just lucky guess. Both have the approximate or about the same volume. The sizes of these 2 balls are about the same. Here's a picture of them both. But what makes it different is the mass. So that's what's changing your density. This one is filled with air, whereas this one up here is filled with stuff. Whatever makes bowling balls heavy, it's filled with it. Okay, so they have the same size, same volume, but their mass is different. And that's going to go back to density. So density of an object is equal to its mass divided by its volume, m divided by v. That's going to give you the unit grams per cubic centimeter, or we know grams per milliliter, because they're the same thing basically. So we're not going to come back and practice all kinds of problems. If you're still not understanding density, I need you to come up to me at this point, because we've been on it for about 4 weeks now. So both balls have the approximate same volume. The masses are different. I don't know why the word dense is blue. Who knows what's going on down there? Ignore that. You're going crazy, laptop. So my afternoon kiddos, you saw this in the lab that we did. Remember, we did 2 separate labs that day. When we have the orange with the peel on, it floats. But when we take that peel off, it gets more dense all of a sudden. We made some predictions as to why that was happening. What we concluded was that the shell itself, or the peel, actually has a very low density. It's very filled with air. So that's why this guy's floating and this one's sinking. So density, more dense objects are going to sink, less dense objects are going to float. Okay. You can use densities with mineral identification. One of these weeks, depending on which class you're in, I think you're moving at 2 different speeds right now, and that's perfectly fine. You're going to use density to identify minerals. I'm going to give you a couple, and I'm going to say it's your job to find out what this mineral is. And that's about all I'm going to give you. So it's your job to use these, 7 tools that I'm teaching you right now to figure it out. What mineral do I have in my hand? And the only thing I'm grading is that name at the end. I don't care how you got there. So density is going to be a key thing that you're going to need to know. You can calculate exact densities. We've done it in 2 different labs now. You can use mass and volume. Mass, you're just going to use a scale, put it on there, read the number. Volume, you're going to have to do the displacement method. And I know we haven't really talked about that word perfectly, but you've all done it. That's when you take a graduated cylinder, you fill it with some water, then you put in the thing, the mineral. You're going to see how much does that water go up. You're going to subtract those 2 numbers. That is your volume. I don't care how much water you have in that graduated cylinder. I gave you the example way back when. If I have a pool or a bathtub and then I put my dog inside of it, what's going to happen to the water? It's going to spill out. I want to know how much did my dog spill out when I put it in. So that's what you're looking at here. I will help you with that if you get to this problem at the end and you're like, hey, Riddle, totally still don't understand this volume thing. I'll help you. But it's pretty easy. Fill it up, put the thing in, how much did it go up? That's all it is. Okay. Or you can get a little lazy and less precise. You can simply pick up the two things and figure out which one's heavier. If I gave you a bowling ball and a volleyball, you would very easily be able to tell me that the bowling ball is more dense or heavier. But for some of these minerals, it's not going to be just that it was heavy or that it was light. It's going to be the difference between having a density of 3.5 and 4. Okay, so sometimes you will need to calculate the exact densities. Other times you can just kind of estimate and you can just pick them up and say, that one's heavier. And the last one we're talking about is special properties. So some of you are already working on your Mineral of the Day project. My afternoon classes, you don't have that assignment, so don't worry about that. You keep asking me about special properties, though. Some of these minerals actually do cool things. So I'm going to talk about a couple of them now. So some of them have special properties that allow you to identify them more easily. One might be texture, or how it feels. Think about clothing when you go to the store. There's all different types of textures out there. There's leather, cotton, wool, silk, that fuzzy one that I don't like, freaks my fingers out. Blech. Okay, so it might be greasy. Greasy is like, at the end of the day when your forehead gets a little slippy and kind of oily, that's greasy. Smooth, okay? There's a lot of things that are smooth out there. A bowling ball is very smooth, as weird as it is. It's hard, but it's still smooth. Graphite feels greasy. So I told you last time you took notes to kind of scribble your pen a little bit and rub your fingers through it. That's greasy. It's slick, okay? So it's kind of a lubricant or an oil. Whereas talc is very smooth. Talc is that baby powder. If you get a rash, I know babies use it, obviously, on their booties, okay? Talc is supposed to smooth out, dry out the area so that baby doesn't get diaper rash. So texture might be a key characteristic. Other ones aren't going to feel like anything, but graphite and talc definitely have a very specific texture. Another mineral might react or do something actually kind of cool. So calcite fizzes and produces a gas when it comes in contact with hydrochloric acid. You have hydrochloric acid in your stomach right now. But obviously I don't want you throwing up all over my tables. That's just gross. So if you get to this part of the lab or the experiment project next week or whenever you're doing it, and you think you might have some calcite and you want to do this test, let me know. We can try it. But you have to be very careful because hydrochloric acid is very powerful. Some might have distinct odors. Sulfur smells like a match. Think about when you light birthday candles or whatever kind of candles. Okay, that kind of matchy smell is sulfur. Kaolinite, ooh, I don't know about that one. We're going to wing it. Kaolinite. Smells like clay. Smells like dirt. Not Play-Doh, like dirt. Okay, so up here, this one's sulfur. That one's going to smell like the match. Down here's calcite. You can see it's bubbling and producing a gas. So that's actually indicating that this is, in fact, calcite. If you would put that hydrochloric acid on something else, it's not going to have that same reaction. Something within the bonds itself is causing that. So that's one key special property. So you can see here that I turned my screen black, so we're doing something else on the screen. So fluorescence is actually a special property as well, or the ability to glow in the dark or when exposed to UV light, ultraviolet light. Okay, so calcite and fluorite are going to do something called fluoresce, basically glow. So when you stick these two under a UV light, which I can provide you if you think you have one of these, it's actually going to glow pretty cool like this guy down here. Obviously, this is like a really cool high definition picture. Yours isn't going to be quite that cool. But they will glow in the dark a little bit if you think you have one of those. Other minerals are magnetic, like magnetite. That's easy. Magnetite is magnetic. So if you hold it up to a magnet, it'll stick to it. Easy enough. Okay, so some special properties actually are very distinct. Other minerals are not going to be magnetic. So if you hold a magnet up to it, boom, you already have your answer, magnetite. And the last one that we're going to talk about is bending of light. So this is a really advanced physics thing, is how light moves and how light bends. But this concept's pretty easy. So if you hold your clear mineral, in this example it's calcite, up to a word, and you actually feel like you have double vision, it guarantees that you have calcite. Other minerals aren't going to bend light in such a weird way, and I'm not going to get into the physics behind how light bends, but if you have light that bends in two directions when it passes through calcite, you can actually see that double image. So if you would put this chunk over anything, a picture of Nuka because he's so pretty, or Nova because she's gorgeous, you would actually see two Nukas or two Novas. Same thing here. So that's one key test you can do as well. You can hold your clear mineral up to words and you can see, does it bend light in one direction? Can you read it once? Or does it bend it in two directions? Can you read the same word twice here? So you can see we read the word calcite, and below it we can also read the word calcite. Okay, so that's a key special property for some minerals as well. So that's what I have. I think that's it for mineral identification. Go back to Google Classroom, figure out where you need to go next.